All right, and we're back. All right, so section 2.4 is everybody's favorite section in calculus. It's called the precise definition of a limit. The precise definition of a limit. Okay, so let's think about where we're at in terms of learning about limits. The first section, it was that just like exploring the idea of like what the heck is even a limit. You know, section 2.1 was that tangent line problem and the velocity problem. Like just real simple, two applications, but we didn't even know what we were talking about yet. Section 2.2 is really, okay, we saw this idea of going to some value, but we didn't have any way mathematically to talk about it yet. So section 2.2 is, okay, how do we mathematically talk about it going to some value? Remember, that's when the only thing that we had was the good old plug and chug method. That was it, right? Just get close, if I wanted to find the value of the function as x went to 1, I just kept running it closer and closer to 1, 0.9, 0.99, and so on, right? And then go from the other end. But the problem with that was that it was like, it's going to get close to there, so we're just going to say that it is, right? And that mathematically is like, ooh, it makes my skin crawl a little bit. It's like nails on a chalkboard, because it's like, how close is close enough? And that idea of just kind of guessing at it and investigating and seeing and estimating what it's going to go to, that was icky for me, right? Ugh, that should make you think like, ooh, that's just gross. But then we did section 2.3, and we said, okay, are there algebraic ways around it? Are there algebraic ways to solve what the limit is actually going to be? And that's when we learned direct substitution, our good friend, direct substitution. And the ability to add, subtract, multiply, and divide all of these functions and all of their limits, right? And apply the limits to them in that way. Okay? So now what we're going to do is we're going to connect back into section 2.2. And because we have this idea of, I want to get close enough to the value so that we can assume it's going to go there, right? Today we will answer that question of how close is close enough. Right? How close is close enough? That's what we're going to be talking about today. All right. So the intuitive definition of a limit in section 2.2 is inadequate for some purposes, because such phrases as x is close to 2 and f of x gets closer and closer to L are just too vague. Right? That's what we were talking about just a second ago. It's just a little too vague for our purposes, for mathematicians' purposes. In order to be able to prove conclusively that these limits are what they are, we must make, oh, jeez. Like a ninja, man. Gosh. I was in the zone. Like I was jeez. Gosh, that really got me scared there. Whew. Precise definition of a limit. Okay. All right, here, let's get back to it. We must make that definition of a limit a little bit more precise. Okay, now, to investigate this, we're going to take a look at this piecewise function. Okay? F of x is equal to 2x minus 1 or 6 if x is not 3 or if x is 3. Okay? Now, we kind of did direct substitution on a problem like this in section 2.3. Not kind of, we actually did. But we had said that we know it's going to be, because x was not 3, and it was happening all around it, we know that this limit is going to act like 2x minus 1, right? We know it's going to act like 2x minus 1. And so we can plug it in using 2x minus 1. And that's what I mean. Intuitively, see ya. Thank you for giving me my scare for the day. Intuitively, it is clear that when x is close to 3 but not equal to 3, f of x is close to 5. Like if I plug that in, 2 times 3 is 6 minus 1 is 5. I know that the limit as x approaches 3 of this function is 5. Because we can just plug it into the top one, right? Pretty simple to see. That's our intuitive definition. Because we know we don't care what's happening at 3, but we only care what's happening around 3. And we know as long as x is not equal to 3, it's going to use the rule of 2x minus 1. Now, to obtain more detailed information about how f of x varies when x is close to 3, we ask this question. How close to 3 does x really need to be so that the function differs from 5 by less than 0.1? Right? So basically what we're stating here is we're stating like an error value. Like we are okay with the final value of that function to be close enough to 5 by less than 0.1. So what's our possibilities for 5 then? Or sorry, for our limit from our output? Our acceptable range is between 4.9 and 5.1, right? Because we're saying that it needs to differ from x, that the function, the actual end value of the function needs to differ from 5 by less than 0.1. Like we're saying in the end, we want our error value, we are acceptable between 4.9 and 5.1. I want to know what x values generate those y values, right? I want to know what x values generate those y values. Okay, so the distance from x to 3, which is just x minus 3, and we can put it in absolute value because distance is never negative. So we say that the absolute value of x minus 3, or meaning the distance away from 3 that x is, and the distance away from f of x is to 5 can be written like this, f of x minus 5, right? When we talk about the difference in between there and taking the absolute value, that is the distance between those two values. So the distance from x to 3 is this absolute value, and the distance from f of x to 5 is this. So our problem is to find a number, and this is a Greek letter delta, that's lowercase delta. We all know delta for the capital delta to be change in, and from science classes, and slope and whatnot. That's the capital, and then this is the, I just draw it as like a fancy looking D, like a curvy looking D. That is the lowercase version of that Greek letter. So our problem is to find a number delta. It's just a variable. Find a number delta such that the distance away from 5 is less than 0.1, right? The distance away from 5 is less than 0.1, and we want to find the corresponding x values. So that means the x values, the difference away from x to 3, it has to be less than delta. Okay? We want to find a range of possibilities for our x value to fall in so that our y values come out to be less than 0.1 apart from 5. That's the goal here. Okay? What we're going to do in this section is called the epsilon delta definition of a limit. What does that mean? That means that I am going to say that we're going to find values so that it's close enough to be some epsilon, which is another Greek letter. Okay, we're going to say it's got to be close enough. How close? Epsilon close. See, I gave you a number here, 0.1, right? I said we wanted it to be 0.1 away. So we could actually run the numbers 5.1 to 4.9. But what if I wanted to generalize that? What if I wanted to give you an option of saying, well, how close do you want it? We can say epsilon close. We can say some some value that you decide how close you want it to be. And if you generalize that, well, then you can say, if you know you want it to be some value, 0.1 or epsilon, doesn't matter, you can say, well, what are those corresponding x values that are going to make that true? And that's your delta. Okay? So what we're saying here is that you guys are going to decide, well, we are going to decide, or the book is going to decide, how close do we want it? And how close, if we say, okay, it can be 0.1 away from the final value, that's your epsilon. What are the corresponding x values that are going to make that true? And the difference between x and your limit as x goes to, say 3 in this case, that's your delta. The difference away from x and your value is going to be delta. So say, that's like saying, okay, to make it 0.1 away, could I plug in 2.75? Or does it have to be 2.8? Or does it have to be 2.9? Or does it have to be 2.99? That's what we're going to be calculating here. Okay? How close do we have to run our x values to 3 so that our final answer comes out to be close enough for what we wanted? Okay? I kind of explained through this. But let me keep showing in terms of this problem here. Now, we saw that 0 was between x minus 3 and 0.1 divided by 2. Now, what does that mean? That means, jump back to this. Okay. I know the difference between, I've got to think about it as like a lower boundary and an upper boundary. I know the difference between x minus 3, which is 0.1 divided by 2 is 0.005. I need to be between there. So this final value, take a look at this. Isn't that 2x minus 1 from our piecewise before, right? Well, just keep evaluating. The final function was 2x minus 1. Okay, 2x minus 6. We can factor out a 2. Yes, you can factor out if it's a positive value. And look what we end with. X minus 3. Well, x minus 3, that was what we were going to, right? We wanted to say the difference between x and 3 was the absolute value of x minus 3. Well, 2 times this x minus 3 is 2 times 0.05, which is equivalent to 0.1. So therefore, what we can say is that if we want f of x to be, the difference between f of x and 5 to be less than 0.1, that means that the difference between x and 3 needs to be 0.05 away. Okay, what is that telling you? That's telling you that if you want your outputs to be between 4.9 and 5.1, you need to calculate x values such that it needs to be 2.95 and 3.05. That's gonna be in your acceptable range. Okay, that's what we're saying here with this delta definition. We're saying that, okay, if you know what your output needs to be, you know what your acceptable range for your output needs to be, you can find an acceptable range for your input. See, like in this case, my acceptable range for my input was 0.05. Now, how did we get to there? We got to there by actually running the value in the function. We plugged in that 2x minus 1 into here and said, okay, can we find an x minus 3 in there? If you can find an x minus 3 in there, then you can finally evaluate what your actual delta needs to be. Okay, I think it would be good to jump to the definition now. That was all kind of lead up to our precise definition of a limit. Let f be a function defined on some open interval that contains the number a, except possibly at a itself. Then we say that the limit as x approaches a of f of x is equal to L. And this is the important part here. Like this is the good stuff. This is again, I will refer to this as the epsilon delta definition of a limit. We could say that the limit as x approaches a of f of x is equal to L if for every number epsilon, and what is it? Epsilon is that ending value. For every number epsilon greater than 0, because epsilon is going to turn out to be a distance. For every number epsilon greater than 0, then there is a number delta greater than 0, such that if we find the difference away from x to a, as x approaches 3, okay, x minus 3, between 0 and delta, then there exists an f of x differencing away from L. The distance from f of x to L is going to be less than epsilon. See, what we're doing here is we're kind of mapping. we're seeing, okay, if I know what my y values need to turn out to be, what do my x values need to turn out to be? If I know the acceptable range for my y values, what is the acceptable range for my x values? That's what we're looking at here. Okay, I think it might be beneficial to jump to this diagram to kind of illustrate you what I mean graphically. Okay? I think it would be best to look at these. Okay. These go in succession here. Just try to follow along. Say we've got some function, some wacky looking function f, and we said we wanted to find the limit as x approaches a. So right here, we're saying that we're okay with an acceptable error of epsilon, whatever that may be. We're making it arbitrary so that you can choose whatever you want it to be, right? Because that's the whole idea of algebra, right? Making it arbitrary so that you can choose whatever value you want. So let's do that same thing here. Let's make it arbitrary. Let's call it epsilon. Now, if we choose an epsilon, that means that my final limit can be epsilon above and epsilon below, right? I'm not saying that that's the full length of the acceptable range. I'm saying that it could be epsilon above or epsilon below, L plus epsilon or L minus epsilon. Now, if we have this acceptable range, then what we are looking for is what are the x values that make that acceptable range true? You know, if we know we want the y values to fall in here, then what are the x values that make that true? Okay. Because f of x is going to lie in here. We need to say, okay, if f of x lies in there, what is the delta to make that true? What are the values of x that will make that true? And what we're going to be calculating is the value of delta. And what is delta? The delta is the difference away from a that you're calculating. So say this a was, 10. Then delta would be an amount above 10 and an amount below 10, just like epsilon was, above and below the limit, above 10 and below 10, that allows me to fall into my acceptable range. Okay? It will say definitively that if you add or subtract delta from a, the y values, when you plug those x values in, will definitely fall in my acceptable range. And what we are saying here with the precise definition is this. We are saying that if you continually make epsilon smaller and smaller, delta exists that will make that epsilon smaller and smaller. You could make epsilon as small as you want it, and delta will exist that will provide you with those y values smaller and smaller. That's why we're saying, okay, if you want to condense epsilon, then there exists a delta that will make that happen. So we can say because epsilon is arbitrary, you can make epsilon as small as you want it. Delta will always exist to make it as small as you want it. All right, now what the heck are the problems going to look like here, right? Take a look at this one. This might be the only problem that we do today. Since f of x is equal to x to the third minus 5x plus 6 is a polynomial. So this is the one that we're discussing here. Sometimes the book starts to provide the solution within the premise of the problem. Since f of x is equal to x to the third minus 5x plus 6. So we're looking at that function. This polynomial x to the third minus 5x plus 6. We know that the limit is, we could evaluate the limit just by doing direct substitution because it is polynomial, right? There's no smoke and mirrors. I know I'm not trying to pull one on you there. I know that we can evaluate the limit to be 2, right? We know that we can evaluate the limit to be 2. What we are going to do here is say, okay, use a graph to find delta such that if x is within delta of 1, meaning I'm plugging in 1, what's my acceptable range above and below 1, so that the y values come out to be within 0.2 of the actual value of the limit, 2. Now, how do I mathematically state that? That's what's down below. I'm going to say find delta so that the absolute value of x minus 1 is going to be smaller than delta. If that's true, then, okay, this whole function minus 2, see, this is where they're starting to provide the solution. X to the third minus 5x plus 6 minus 2 has to be less than 0.2. Like if this was like a quiz or test problem, I would not give you this. Like you would have to remember that. Okay? Now how do you come up with that? You say, well, you know that you need the value of the function the final output of the function, because that's f of x, minus the actual true limit, that needs to be less than 0.2. You follow me there? That's what you want to, you will need to come up with that on your own. But honestly, that's super easy. Because you're just taking the value of the function, you subtract away the true value of the limit, and then you set it less than, make sure you put it in absolute value, and then you set it less than your epsilon. And in this case, we're choosing our epsilon to be 0.2. In other words, find a delta that corresponds to epsilon being 0.2 in the definition for this. Okay, so how do we do that? Well, I guess I have to just run this algebraic, right? Okay. Now, I hope we remember from Algebra 2, maybe Pre-Calc 2, I don't know. Is this going to be an and or an or? Less than. Remember that trick? Didn't I teach you guys that? Yeah. If it's an absolute value, it's less than or great or. If this was a greater than, this would be an or and point out. Spoiler alert, these are all going to be ands, okay? Because that's the definition of the limit. It's got to be less than that. So that means that this is negative 0.2 plus 4, right? I'm just kind of evaluating that. Which makes sense. That now I'm just kind of shifting that up. So I want it to be less than, to be in between negative 0.2 to 0.2. Oh, oops, sorry. Rewind. Forget what I said there. Okay. Okay. Because I want to illustrate it in this way. I'm going to add the 2 to both parts on the outer sides. Because I want to try to keep that function the same. Add the 2 over here. This is 1.8. Honestly, the solutions would come out exactly the same if I would have done it just the way I had said. But I like this better. Why do I like this better? Because this is truly showing you that the value of the limit needs to come out to be between 1.8 and 2.2, right? The end values of the function need to be coming out to be 1.8 and 2.2. Okay, now I just need to figure out, it's right there. Get out of there. Let the cat out of the bag there. I just need to figure out where these things are happening, right? I need to know this. And then this. I need to know where those intersection points are occurring. Because where those intersection points are occurring gives me my x value. Now, how do we do that? Well, I think the easiest possible, this is not quadratic. If this was quadratic, I could just move that over and then use the quadratic formula. Done. But this is cubic. So the only way to do this right now is to put it into our calculators. x to the third minus 5x plus 6. And then say, okay, I want 1.8. Zoom 6. Okay, now be careful here. I want to keep getting closer and closer to 2, right? So maybe it might be good to change my window so that my x minimum, let's go, oh no, my y minimum, let's go 0. And my y maximum, let's make that like 4. Oh, that didn't that didn't really do much, did it? Okay. But what I'm looking at here is I want to find my intersection points. Second calculate intersect. Okay. Now I wanted to get closer and closer to 2. So my first curve, enter. My second curve, enter. Now when I guess, I want to get closer and closer to 2. Yeah, my output there. There it is, 1.45. 1.45 is my x value. Oh, I think it was right there. Get these out of the way. It does. Now, I do that same thing with my upper boundary to do 2.2. I know I'm running out of time. And I do second calculate intersect. Oh no, I'll start here tomorrow. I get closer to 2. It's 1.63. So I know I just got to be between 1.45 and 1.63 for my x values. We'll talk about what that means for delta tomorrow. Because that's not truly my delta. We'll pick up right there tomorrow.